Well, hello everyone, and welcome to the last session of the day. And I'm Peter Cameron. I'm very pleased to be chairing this session. The speaker is my old friend Persi Diaconis. Persi is a professor of statistics and mathematics at Stanford University, but you'd rather hear him than me, so I'm not going to tell you all the things that you can look up in Wikipedia. Let me just say a couple of things about Persi's lectures. The two things I really like are, first of all, he does not admit any barriers between different parts of mathematics. And secondly, he'll always do some magic for us, pull a rabbit out of a hat. And so you're in for a great time. Persi is going to talk about gambler's rune and geometric analysis. So Persi, over to you.
So am I on now? Does everybody, that's where I'm supposed to be? And can people see gambler's rune and geometric analysis? Great. Good day. So this is a talk about some work that is ongoing, but lots of open things, but lots of things we know. It's joint work with a group of friends, Stew Ethier, and then Kelsey Houston Edwards and Laurent Solifcost for the geometric analysis part. And I started this kind of quantitative analysis of quasi-stationarity. I'll explain those words with Laurent Miklo. And I want to start at the beginning, and that's with this problem of the classical problem of gambler's rune. And everybody here knows Zhao. And suppose that Zhao and I are gambling, and we're gambling by flipping a fair coin. And poor Zhao starts with €1, and I start with 99 euros. What's the chance that Zhao wins all the money? Each time the coin comes up heads, he gets €1 from me. Each time the coin comes up tails, he gives me €1. So if the coin comes up tails, the first flip, he's wiped out. But it might be that it comes up heads and then tails and heads a few more times, and then he wins. So what's the chance that he wins all the money? That's the classical problem of gambler's rune. And of course, the chance is very small. If I start out with 99 and he starts out with 1, it's very unlikely. Well, how small? And the answer is surprising to me still. The chance that Zhao wins all the money is 1 in 100. And of course, that is small, but it's not exponentially small. It's 1 in 100. It could happen, does happen. If he starts out with A and I start out with B, the chance that he wins everything is proportional to his starting amount, A over A plus B. That's a result that Pascal and Fermat derived at the very start of probability, 1665. One can also ask how long the decision will take until either he gets wiped out or I get wiped out. And the waiting time, Demov showed, is proportional to the product of the two starting amounts, A times B. So if we started balanced, if he started out with 50 euros and I started out with 50 euros, it would take quite a long time. It's 2,500 flips. And if he starts out with 1, and I start out with 99, until the decision time comes, the wait is 99. So that's classical gambler's rune. Now, what I want to tell you about today started in the following way. I teach a graduate course on the mathematics of gambling. And it's a lot of fun, but it's a real course too. And I had a guest speaker who is Chris Ferguson, who's a great poker player. He won the World Series of Poker, I think 3 or 4 times. And when you win the World Series of Poker, well, it's something like you win $10 million. So he's a rich guy, and he was giving a guest lecture in my talk about about poker. And he said, you know, it's important for me. There's a gambler's rune problem that you guys don't know how to solve. I said, oh, yeah? Come on. Now, Chris is no pushover. He has a PhD in computer science, and his dad is Tom Ferguson, who's a great statistician. So I listened up, and here's Chris's problem. It's the problem with three gamblers. And my three gamblers are Zhao, again, and he has A units. And Peter, my announcer, has B units. And there's Persi, who has C units. And the game is the following. Each time we pick a pair of us and at random, uniformly, among the three possible choices. And then a fair coin is flipped and a unit is transferred as it comes up, heads or tails. And then we pick another pair and flip a coin again. Now, of course, it's a finite game. And by the luck of the draw, eventually, one of the three of us is wiped out, and two remain. And then those two do the usual gambler's rune until one player winds up with all the cash. And so that's the three players gambler's rune. And he wanted to know what are the chances of the 6 elimination orders? That is, I'll use this notation. The elimination order 1, 2, 3 means the first player is wiped out first, and then the second player who had B units is wiped out second, leaving the third player with all the cash. So there are 6 possible ways that could happen. What are the chances, and how do they depend on the starting capitals? That's the question he said we didn't know how to solve, and there's some sense in which he's right. Let me give you the motivation, his motivation. In poker tournaments, and the World Series of Poker is played once a year, but there are hundreds of poker tournaments every week. At the final table, the last 3 players have stack sizes, and whatever else happened, a new round is starting, and they have stack sizes A, B, and C. The payoffs, however, whoever wins all the money, you don't get all the money. You get a fixed size prize. In the current World Series of Poker, it's $10 million. But as you'll see, the stack sizes are very, very different. So the decisions that you make don't necessarily, of course, you want to win, but your payoff is not the amount of money that you're going to win. Your payoff is a fixed prize, and there's a first prize, second prize, third prize. So, what's your expected win for any given decision? How should you play to optimize your expected value? And what about if you have to settle? That's not something that gets so much publicity, but professional poker players, they're huge amounts of money. And suppose that we have A, B, and C, and Peter and Joe and I say, well, I don't want to gamble for that amount of money. Suppose we settle up. How should we settle, and how should that depend on A, B, and C? So all of those questions depend on these probabilities. So that was some motivation for this classical problem. Just to make contact with reality, here are some numbers. In the 2019 World Series of Poker main event, at the time the 4th place finisher was eliminated, the 3 remaining players had these chip counts. And this is actually true. So this is $67 million. And the next guy had $120 million, and the leader at the start had that amount of money. It's helpful to normalize things so that the what's called the big blind is the ante, the kind of unit that is bet. And at this stage of the tournament, the big blind was $2 million. So if you divide by $2 million, the number of big blinds in this amount were these amounts. So that's, well, That'll be something like A, B, and C. The actual payoffs, the winner, it happened to be that the guy with the biggest starting chip counts won, and he got $10 million. And the second place finisher, the guy who was eliminated just before the end, got $6 million, and the third place finisher got $4 million. And so that's an example. The math I'm going to tell you about, the actual probabilities of the 6 elimination orders from these numbers, and I'm going to multiply them by 5, so I'm working with integers. So if A, scaling doesn't change things, if A, B, and C are these 3 numbers, 169, 301, 817, these are the 6 probabilities. So, of course, the most likely order is that the guy with the smallest amount of money is eliminated first, the guy with the next smallest amount of money is eliminated next, and leaving the guy with the biggest amount of money eliminated last, and he gets all the money. The actual order in this particular round was 213, and so that's the second most probable thing. That's what happened. Okay, so that's some background for the math problem that I'm going to talk about. Here's a different way of thinking about it. Test your intuition, okay? Suppose that we do the following. Zhao and Peter each have €1, and Percy has N-2 euros. What's the chance that I'm eliminated first? Well, of course, it's small. But how small, and how does it depend on N? Just to think about it. Well, naively, you might think, well, Zhao and Peter each have 1. Let's just lump them together. That's like one person with 2 units, and Percy has N-2. So, of course, Percy's probably going to win, but the chance that, Zhao or Peter wins is going to be, by ordinary gambler's rune, what I started out with, will be, perhaps you might think, something like 2 over N. Might be. That's many people's first reactions to this question. In the world of gambling, there is a scheme that people use. It's called the ICM, Iterated Card Model, and that predicts, or that supposes, that the chance that the big player is wiped out first is 2 over N squared, and since hundreds of gamblers use that in the real world, maybe that must be right. Hundreds of gamblers can't be wrong. Yeah. The math I'm going to tell you about will show that, in fact, the answer is constant over N cubed, and the constant is this constant. This is a conjecture, this part. This constant is this. And to many, many decimal places, that seems to be this strange number, and we can't prove that, but it's surely true. And I want to trick you into thinking about it as we go along. So there are questions. Intuitively, the right answer is constant over N cubed. Where does the N cubed come from? Why is it N cubed? And if you think, well, there's probably just some simple reason, I'll warn you that if I had 4 gamblers, the answer is constant over N to a power. We don't know the power, and as far as I know, the power is an irrational number. So it's not going to be so easy to say, oh, the N cubed is because of this. Well, anyway, I don't know where the N cubed comes from. So that's coming. Okay, so that's gambler's rune. Now I'm going to abstract. So the general problem is this. We have a graph, and that has a vertex set X. I'll be more specific when I need to be. And a set of edges. It's an undirected, simple, connected graph. And then I have what I'll call a domain, which is just a finite subset, this subset U, and it's connected, so I can get from any place to any place else by steps within the graph. And a random walk is you're at a vertex and you pick one of your nearest neighbors with, say, equal probability, and then you go there. Now, since this is finite and it's a big graph, eventually you'll get out. You'll go outside, and so that's the abstraction. Start a random walk at X contained in this domain. Let capital T sub U be the first time you hit the boundary. That is, that you exit the region. Three natural questions. How long does it take until the game is decided, until you hit the boundary? When you hit the boundary, where do you hit it? That is, does Zhao win, or does Peter win, or does Persi win? When you hit the boundary, where do you hit it? And another question, which is very natural, suppose that you've been walking around for a long time and you're still in U. Where are you likely to be? In symbols, let me parse this phrase. So I started out at X. What's the chance, given that you haven't been absorbed up to time T maybe is an hour, that the random walk is at Y, where X and Y are in the region? That's called the quasi-stationary distribution, and it exists. And so if life has been going on for a while and we haven't been wiped out, where are we likely to be? We're interested in answers to these questions, and we'd like to know how they depend on where you start. If you start very close to the boundary, that's different than if you start in the middle. So that's the general context that these Gambler's Rune problems fit into. The questions arise in biology, where creatures are born and you move around, and the number of A's, B's, and C's that there are. Certainly, there are basic questions in physics and in financial math, and many other areas. These are called first hitting times in probability, and absorption times, and that sort of thing. The Gambler's Rune problem, if I have three integers, A, B, and C, well, each time, you can change A, B, and C by one. And so if you can, since N is fixed, the total amount of money is fixed, I can just graph A, B, and A and B. And so the state space would be, this is U here. The open circles, this is when N is 6, is where there's still something to decide. This is when one of the players are eliminated. Here, a different player is eliminated. Here, a different player is eliminated. And then the three times when the game stops are these three corner points. Okay, so that puts the Gambler's Rune problem in this problem of first absorption. Okay, I want to this talk was called Gambler's Rune and Geometric Analysis. So let me just segue into a sentence of geometric analysis. So I've got my domain U, so I'm just in the graph now, and let K sub U of XY be the chance that if you're at X, in one step of your walk, you're at Y. Here, X and Y are both in U, okay? So forget about going outside. This matrix, it's just a finite matrix indexed by X and Y. It's positive. All the numbers in it are non-zero or positive. And I'm assuming it's connected. My domain is connected. So the Perone-Frobenius theorem says there is a Perone eigenvector, phi naught, which is a positive vector, and a Perone eigenvalue, beta naught. And I'm thinking of my eigenvectors as right eigenvectors, column vectors. And so the eigenvector equation says that if I take this matrix and I multiply it by the column vector phi naught, if I look at the X entry in that matrix, that should be beta naught times phi naught of X. So the Perone-Frobenius says that positive connected matrices have Perone eigenvectors, and an easy theorem in the subject, and I'm going to try to parse this statement. So let me go through it slowly. The statement is the following. Look at the chance. I started at X, which is in my domain U. and look at the chance that at time t, I'm at y, okay, and x and y are both in my domain, and I'm going to assume that I haven't been absorbed, that I've stayed within my domain, and so the absorption time is bigger than L, and then I'm going to let L go to infinity. Okay, it's a little theorem that limit exists, and what this represents is what's the chance that you go from X to Y in T steps, given that you're never absorbed. Okay, that's what this means, and the little theorem says that you can express this probability in terms of the teeth product of the matrix K sub u of xy, and then you have to tilt it by these eigenvectors and this eigenvalue. So this limit can be expressed, and these are the Perone Eigenvector values at x and y, and this is the teeth power of beta naught. So this whole matrix on the right, if you sum this in y, you've summed it in y, you would sum it this in y. That's the eigenvalue equation. That would get you beta naught of t, and that would get you beta naught of t. This sum in y would get you beta naught of t times phi naught of x. That would cancel. So this is a stochastic matrix, and I'll be calling that matrix K upper T sub phi naught of xy. The chance that you go from x to y, given that you're never absorbed. This matrix is an ordinary Markov chain. That is, it's never absorbed. It has a stationary distribution. It's called the Doob transform, and the reason is that the Perone eigenvector vanishes at the boundary. So there's no chance of exiting, and so. The stationary distribution of this transformed matrix is proportional to the Perone eigenvector squared, the coordinate y squared. So these are all little linear algebra facts. They really are elementary facts. And now there are two expressions on the slide. The reason I'm introducing this, what's the chance of going from X to Y, given that you're never absorbed, is that the quantity that would be more of interest, what's the chance that you're at Y, given that you haven't been absorbed up to time T? That limit also exists, and it's proportional to just the ordinary Perone eigenvector. That's called the quasi-stationary distribution. You will be absorbed eventually, but if you haven't been absorbed up to now, and now has been going on a long time, that's this quasi-stationary distribution. As an example of the math that's coming, the rate of convergence in this limit controls the rate of convergence in the problem we're interested in. That is quantitative, what's the rate of convergence of a Markov chain to its quasi-stationary distribution? And just the way the theorem looks is this way. This is this Doob transform chain, and I'm looking at what's the chance that you go from X to Y in T steps. And I'm taking the ratio of that to its stationary distribution. So as T goes to infinity, of course, that goes to 1, subtract off 1, and suppose you got your hands on that and you knew that it was small, that it was less than epsilon for all X and Y and all sufficiently large T, so that you got your hands on this rate, it was less than epsilon, then the quasi-stationary distribution is also less than essentially epsilon, twice epsilon. So you can transfer from the Doob transform chain, which is an ordinary Markov chain, not absorbing, to the absorbing chain. And the same transfer happens for all of the questions. That is, I had 3 questions. How long does it take When you hit the boundary, where do you hit it? And what's the quasi-stationary distribution? If you understand the Doob transform chain, you can answer those questions. So what that gets you into is, in order to progress in this kind of problem, given a graph, a vertex set and a set of edges, and a domain U, you have to understand what's the Perone eigenvector, what's this eigenvalue, and what does this Markov chain look like? I mean, that's where the math gets you to. And those questions are quite challenging, but with the geometric analysis I'm going to tell you about, we can answer them, and under conditions. In order to state anything that looks like a theorem, I'm going to have to put conditions on the graph, geometric conditions on the graph. It has to be not too crazy. A graph can be, I have Peter Cameron on the screen, right? I mean, a graph can be any crazy thing. Sorry, but I'm going to need conditions on the weights. I haven't talked to you about weights. They're coming. And I need my domain to be not too crazy also. So I'm going to, here's my plan for this talk. I'm going to tell you some conditions, and those are conditions that are borrowed from analysis, from geometric analysis, from PDE, but I'm going to say them first in English, and secondly in the language of graphs, which is as close to English as I get, and then I'm going to tell you what they say about the gambler's Rune problem. So that's my plan. So here we are talking about graphs. So a graph. I have a vertex set X, and it can be absolutely arbitrary. It could be finite, could be countable at the moment. I have some set of edges. I'll call them E, and I'm going to take the edges to be undirected. I'm going to make my big graph be connected, and I'm going to suppose it's locally finite. So every vertex has at most finitely many things. It's useful to capture real scientific problems to put weights every place. So I'm going to have a weight function, pi, the stationary distribution, as it were, which is just assigned to each vertex of the graph. So it's a positive number on each vertex of the graph. And similarly, I have a weight function undirected, mu xy is mu yx. I have a weight function on each edge of the graph. Okay, so those are positive weights. And it's useful to assume that the sum of the weights coming out of X is less than pi of X. Just I'll make that assumption. And with that assumption, I can define a Markov chain, a way of moving around on the big graph X. And it's just the following way. If you're at a vertex X, you look at your neighbors, the y's that you're connected to, and you pick one of them with weight proportional to mu of xy. And the actual recipe is the chance of going from X to Y in one step is mu of xy over pi of X, and that's less than 1. And if there's anything left over, when you sum this in Y, it's less than 1. If there's anything left over, you just say, I'll stay at X with whatever probability is left over. So these ingredients, and it could be that all of the weights are 1. I mean, but these ingredients define a class of Markov chains, a class of moving around on this big graph. So that's the graph notation. A first analytic assumption is ellipticity, as it's called. I want an elliptic operator, but all that means is that my mu's aren't too crazy. There's a fixed delta, a half, a tenth, 100. Delta is fixed, positive number, such that pi of X is less than or equal to delta mu of xy, and that's the usual ellipticity in differential equations, but that's what it translates into in this condition. And so, if all the weights were 1 in a normal kind of graph, delta could be 2 or something, or a half or a tenth. Okay, delta is delta. Okay, so that's my graph setup. I have two conditions on the weights, and I'll go through those as slowly as I can. The first is called the doubling condition. And let me at least say it, it's a simple condition. There's a positive constant, the doubling constant, such that for every starting point and for every ball, a ball has a center X and the ball has a radius R, the mass, the sum of the pi probabilities of the points in the ball of radius 2R is controlled by the mass in a ball of radius R up to this doubling constant. Okay, so that's an assumption. And roughly speaking, it says that the graph is something like, a finite dimensional lattice. Of course, it doesn't have to be anything like a real lattice, but, roughly, it shouldn't grow exponentially. The volume of balls shouldn't grow exponentially. So this condition, all the graphs that we need, all of the Gambler's Rune graphs certainly satisfy the doubling condition, but that's a familiar condition. So that's a first condition. The second condition will look strange unless you're an analyst, but okay. We call it the local Poincare inequality. And it's, again, I've got my graph. There should be what's called the Poincare constant, C sub p, a positive constant, such that for any function and any ball, any x and any r, if I average the function over the ball around its average, so this C sub b is the average of the function over the ball, I subtract that from the function. So this is the variance of the random variable constrained to the ball. So if I look at the variance, that should be less than or equal to the sum over z and z prime in the ball squared times this, the chance of going from z to z prime. And then in front is r squared, the volume of the ball, and the Poincare constant. So this inequality is called the Poincare inequality in analysis, and it's called the Poincare inequality because Poincare discovered that's the way you bound the eigenvalues of the Laplacian on domains, and it's local because I not only need it for the whole space, I need it locally. Okay, so that's not so easy to get your head around when you first look at it, but it's pretty easy to work with. What you have to do in order to prove a Poincare inequality, given a graph, we've got to show that there is a Poincare constant. What you have to do is just choose a path between every pair of points, x and y. You have to choose a path, and you have to get your hands on what we call the covering number for a choice of paths. Given an edge in the graph, given a choice of paths, given an edge in the graph, how many paths use that edge? That translates into this. So you can really bound Poincare constants for natural graphs. And anyway, those are two assumptions on the geometry, on the weights. One is the doubling assumption, and the second is this Poincare. Okay. Finally, there are conditions on my domain U, okay. So my domain is a finite connected set in X, just so that I can get someplace. A domain is called an inner uniform domain, and there are two parameters, little alpha and big A. If for every pair of points in the domain, you can find a path. The path I'll call gamma xy from x to y. The path is x0, x1, etc., which are edges inside the domain, which join x to y in U. And it should be that the length of your path is comparable to the distance between x and y in the domain. It might be that you have to choose a funny path. And the thing you're aiming for as you want the distance along the path, you're going along the path from X to Y, look at how far you are from the boundary, from outside. You want that distance to get bigger and bigger as you go along the path up to the middle. And so this isn't so easy to parse, but let me show you a picture. We call these shapes bananas. You have 2 points, X and Y, in the domain. And as you go along the path, the distance to the boundary should get bigger and bigger until you get to the middle of the banana. And of course, that can't be at both ends. So this domains which satisfy this condition are called inner regular domains. And all of the domains that we talk about will satisfy this condition. If you take a lattice, an ordinary lattice, ZD, and if you take a convex set and intersect it with the lattice, that's fine, the kind of triangles I was drawing, but it doesn't have to be that way. This is an example of an irregular domain where here, these are bad points, and this is my U. And if I hit one of these central points, or if I hit the outside, I die. Okay, and how long does it take? And so the irregular domains can be somewhat weird. They can't be very weird, but anyway, it's just, I want to state a theorem, and it's easiest if I make some assumptions on the domain, and the assumption that, and again, these are all taken from conformal geometry and PDE. They're standard definitions, but adapting them to graphs, well, it's a several years' work. Okay, so I agree, if you're following along, that's a lot of assumptions. I don't want to argue that. Okay. But with all of those assumptions, I can state a theorem. And then I promise you I'll come back to real examples. So here's a theorem with all of that notation. So suppose I have little alpha, that's my little alpha in capital A, or my constants if I have an irregular domain, and assume my graph satisfies ellipticity and doubling and local Poincare, and that U is an alpha A uniform domain. Then the Perone eigenvalue, beta naught, is less than or equal to 1 minus a constant over the diameter of the domain, the length of the longest, the furthest separation. And what that says is that the absorption time of the random walk will be of order r squared. I mean, that this translates into how long does it take until you die? Well, it's of order r squared. And this constant c is explicit, but I have the good taste not to show it to you. It depends on all of the parameters that are floating around. It depends on it explicitly. We also have control over the Perone eigenvector. And one way of saying this, these are statements, well, these are theorems, this is called a Carlson type estimate, Leonard Carlson, who derived it in continuous settings. But the ratio of the eigenvector doesn't vary too much. It varies like a reasonably well-controlled polynomial in the distance between x and z, and that allows you to estimate the eigenfunction by comparison with nice domains. That is, if you neaten up the domain and make it all square, then we can write down the Perone eigenvectors of a nice domain, and this allows you to compare with nice domains and really get pretty useful assertions about the Perone eigenvector. The third thing, and it's the worst, but I'm going to say it anyway. Suppose that I'm in the middle of the domain and a central point, x star, it just means that that if I take a ball of half the radius, I'm inside the domain, and if I take a ball that's 3 times the radius or something like that, or 3/4 of the radius, I cover the domain. So suppose I have a point in the middle of the domain, and I'll use this notation. What's the chance, given that I started at X star, the middle of the domain, that I haven't been absorbed up to time t, that's this t, and that the Markov chain at the absorption time haven't been absorbed before, but that when I'm absorbed at Y, which is a point on the boundary. So that's all the information you could want to know. That's the joint distribution of how long it takes to be absorbed and where are you absorbed. And that's a thing that if we knew it, we could do everything. And without trying to parse this so well, this thing that we want to know is upper and lower bounded by quantities that we have our hands on. This is the eigenfunction. This is the size of the domain. This is the chance of going from the thing, just Y is outside the domain. We'll pick something inside the domain that leads you to Y. That's this chance. And these two things are the same. Everything's the same. It's just there are 2 different constants here and here. So we have reasonable upper and lower bounds on this quantity that describes what I need. Okay, so I know that's very technical. Let's go back to Gambler's Rune. Okay, so all of that work is what it looks like if you try to abstract, and what happens when you take your big machine that you built and you apply it to a real problem. Okay, so these are my Gambler's Rune probabilities. I'm graphing things in 2 dimensions. This is A, and this is B, and my Gambler's Rune. There's 3 of us, A, B, and C, and of course, C is N minus A plus B, so these are all okay. And this is if the starting point is in the middle, so like N over 3, N over 3, and by symmetry, I want to know, I want to estimate the chance that, let's say, Zhao is eliminated first, sorry, Zhao, or that Peter is, or that I am. By symmetry, if you know how to calculate the chance that starting inside this triangle that you're eliminated here, everything can be reduced to that. So my boundary is just going to be this bottom edge. And so the question is, what's the chance if you start here? So here, the chance, here we're all we start with all the same amount of money. In this scenario, X, A and B are small, they're both 1, and so C is N minus 2. So in this scenario, C has it all, and in this scenario, B has it all. That is, B is very big, and A and C are small, and still one would like to know what's the chance that when you're first absorbed, you're at Y, and then of course you do ordinary Gambler's Rune at Y along this axis until one of them winds up with all the money. So that's the special case. This is an irregular domain and everything is just fine. All the weights are a 1/6 and all of that. These are the kinds of theorems that come out of that mess that I showed you. In the first case, if you start in the middle, the chance that you first hit the boundary at Y, well, it's proportional to Y squared, N minus Y squared over N to the 5th. And I use this double wiggle notation to mean there are universal constants, and it's upper and lower bounded between 2 positive constants in this, and the constants are explicit. If C has it all, that was this case, the answers are different. What's the chance that you're in Y? Which Ys are most likely to hit? That's the kind of answer. And this is the one that we're going to need to do the question I asked. That this is if B has almost everything, the chance of being absorbed at Y is this. These estimates, these asymptotics, are all uniform in Y. The constants don't depend on Y or N. Okay, so let me use this to show you this theorem that I began with. What's the chance that if Peter and Zhao each have 1 and Persi has n-2, that Persi goes broke first? Well, I claim that chance tends to small. It tends to 0 like a constant over n cubed. And the argument goes this way. Once you translate it to the triangle, you may as well say that the big player is the second player. The labels don't matter. So the first player and C each have 1, so the big player is the second player. What's the chance that if you start that way, this says that the second player is eliminated first, so that you hit that boundary there? What the theorem says is that that's proportional to y squared, n minus y squared over n to the 8th. Okay, well, rearrange that, write it as 1 over n to the 4th, and put 2 n's here and 2 n's here. Okay, and now sum that up in y, because any such y, once this happens, the big player is eliminated. Once this happens for any y, the big player is eliminated. So sum this up in y. Remember, the estimates are all uniform. So the chance that the player 3 goes broke first is just this sum, and I'll make a Riemann sum out of it. So I'll take one of the n's and put it here, and that's the beta function. That's a Riemann sum approximation to the beta function. So that goes as a constant over n cubed. So that's the way these tools are used to get answers that you can interpret in English. And so that's a long story for this. Here are some numbers. When these, of course, are very hard to, but this is what's the chance. I chose an order for the elimination. So if n is, these are different n's, and you can do the numerical analysis and get exact, or as exact as you want. You can actually get exact answers. And the chance of the elimination order 3, 2, 1, that means the big player is eliminated first, and then 3, 2, 1 or 3, 1, 2 are equal, because 1 and 2 each had a unit, but say this starting order. So the chance as n increases, decreases. But if you multiply these numbers by n cubed, what you can see is that they stabilize, and they stabilize quite rapidly. And this is that crazy formula that I showed you with the pi's and the gamma of a third and et cetera, like that. That's these numbers. And I'm only telling you 10 decimal places. We have them to 100. Stew is a fanatic for exact computation. Okay, so that's where that particular number comes from. So let me summarize where we are. What I wanted to tell you is the following. There are simple problems in classical probabilities. These questions could have been asked by Fermat and Pascal that are easy to understand, Gambler's Rune with 3 gamblers, and that are open. For example, I can't prove this. I can't prove that the chance with starting 1, 1 and n minus 2 that the big guy is eliminated first is asymptotic to a constant over n cubed. I know that it's between 2 constants times 1 over n cubed, but that's different than being asymptotic to a constant over n cubed. And of course, in this case, I have a guess at what the constant is. I don't know that. I don't know with 4 gamblers the math gives you something, of course, but I don't know how it goes to zero. I know more than I'm telling you. There's a good chance that this question mark is 5.37282 or something like that, but I don't actually know that. A very interesting question is the scaling conjecture, which is if you triple all the numbers, the chance of the given permutation shouldn't change. That's certainly true in that we compute exactly and we know it's true. The scaling conjecture, it's not so easy to make a sharp mathematical conjecture. I'll make one here. What's the chance if you start at ABC that the elimination order is sigma? That should be approximately the same if you triple all the numbers or multiply them all by n. More precisely, there are many way of making it precise. I believe that this is true for all ABC and all n and all sigma. The difference between these two numbers is tiny. They're not the same. It does change, but it changes way down there. And so I've been using that. Gamblers use that all the time. It seems to be true. We can't prove it. The techniques that I told you about are drawn from far away from graph theory and probability. They're drawn from geometric analysis, conformal geometry, and PDE. A message is they can be translated into English, if you believe I spoke some version of English, and adapted to finite graphs. That's taken us a lot of work. There's no real reason to look, but here are many things that I haven't told you about. The geometric domains, I told you about a very special case, inner uniform domains. There are harder domains, more general domains that are called John domains. Everything kind of works for those. A key ingredient, or what analysts call Whitney covers, I'm not going to try to tell you what those are, but our paper is just filled with colorful pictures of them. I try to tell you about Poincare inequalities. There are refinements of those that are important. And these are all things that I would love to tell you about, but they're written about. Suppose you said, gee, that looks interesting. I'd like to know more. Here are 3 places to look. The Gambler's Rune paper is a paper that is about to appear in Statistical Science, Gambler's Rune in the ICM. The math behind the constant over n cubed type theorems is in a paper I wrote with Kelsey and Laurent, Gambler's Rune estimates on finite inner uniform domains, that appeared in the Annals of Probability this year. And the analytic machine that Venn diagram alludes to is called Analytic Geometric Methods for Finite Markov Chains with Applications to Quasi-Stationarity. All my papers are on my homepage. Type Persi into a search engine, you'll find me, and all my papers are on the archive. I'm very thankful to the Portuguese Math Society for allowing me to give this talk. I'm very thankful to Peter for introducing me, and I'm exponentially thankful to Zhao for everything he's done for me. Thank you very much. Thank you.
Well, thank you, Persi. There is time for a question or two if anyone has one. I don't see any questions. No questions yet in the chat. So I take it from that everybody is just still reeling from this.
Sorry, yeah, no, well, I have the following. I know the difference between a technical talk and a friendly talk, and this had some friendly aspects, but it was technical. But the Portuguese math community is a healthy, grown-up, sophisticated community. I didn't want to give a talk for children for this group. I hope I didn't go over the boundary, but you guys are wonderful mathematicians, and I try to talk math to you. So That has its costs, but I hope it has its benefits too. I was asked to say, and Peter was asked too, to say that I'm going to be in meeting room 1 after this talk. So if people want to come and say hello or ask anything, I'm going to be there for some time. So I hope that people are able to join. I hope I'm able to join. It shouldn't be so hard, but good.
Okay, well, so it just then, what exactly is so hard about the number being 4 or more? Bernardo asks.
So the question is, what's special about 4? And well, of course, yeah, we don't know. So that's the question. That's my question to you. You can't ask my question to you and ask it back to me. No, that's my question. That is, in one dimension, it's sort of it's 1 over n, and in 2 dimensions, it's 1 over n squared. And if you went to 3 dimensions, if you went to k dimensions, it's 1 over n to a power. But those powers seem to be strange, irrational numbers. And I don't understand. And I actually, so that I don't understand. The numbers are, they come up in other places. And one thing I didn't have a chance to tell you, I thought I might, but I didn't, is a big part of the math that we did in the paper with Stew was very, very careful numerical analysis, get the right numbers to infinite precision, get the right numbers to 20 decimal places. And that's very interesting too. I just didn't put it into this talk, but there are interesting techniques in numerical analysis, sparse matrix analysis, domain decompositions, all of which we used, and if you need them, the numerical analysts really do have things to say, and it's full of ideas, and many of those ideas are in our paper. So I have good numbers, and I kind of know, I have a pretty good guess at what it is for n. I mean, but it's some irrational number, and I have no understanding of what it is yet. I can express it in terms of hitting probabilities for Brownian motion, and it comes up in the same exponents come up in other problems, but we don't know what they are. So that's intriguing, right? That's what I wanted to sell you. So okay. I agree. What's special about higher dimensions? Chris Ferguson, when you start a poker tournament, there can be 10 players, and how do the numbers depend on it could be much larger of interest too.
Okay, well, I think our time is just about up, so it remains for me to say a very big thank you to Persi for that lecture, and I hope you will all join me in agreeing with that. You are all invited to meeting room 1. Persi will be there, hopefully. And there are a few more questions in the chat, which we're not going to take now, but you're very welcome to go to meeting room 1. And I'm sure Persi would be happy to chat about these things in that informal setting. And finally, just to remind you that this is the end of day 4 of this lovely meeting. Day 5 begins at 9 o'clock tomorrow morning, so be there. So thank you very much.
Bye.